If you're going to understand the pH scale, you need to understand a little bit about water. And water will actually react with itself and do what we call self-ionization. And you can think of it as one water molecule doing this or two water molecules doing this. But essentially what you end up with is that water, to a very small extent, will split and create H plus ions and OH minus ions. If you do this with two water molecules in the reaction, you end up with H3O plus, a hydronium ion, and a hydroxide ion. Okay. Now, H plus and H3O plus is considered to be the same ion, really. If you have protons in a solution with water, they will bind with water to make H3O plus. So if we looked at an equilibrium constant expression for this process, this self-ionization process, we'd set it up like this. Kc equals H plus times OH minus, and then on the bottom would be water. But since the concentration of water is essentially constant, since there's so much more water than these other things, we can pretty much take it out of the equation, and we're left with this, what's called the Kw, or the ionic product constant of water. And it's equal to the concentration of hydrogen ions times the concentration of hydroxide ions. Now, the name's pretty good. It's a constant, and it's the product of the ion concentrations, right? It's when you multiply these two things together, that's what we get for Kw. And at 298 Kelvin, or 25 degrees Celsius, the Kw of water has been determined to equal 1 times 10 to the minus 14th. Okay, well, if we think about the fact that anytime water splits, it's going to make an even amount of H plus and OH minuses. So in neutral water, these two concentrations should always be the same. So if I replace the concentrations with X in this expression, Kw equals hydrogen concentration, hydroxide concentration equals 10 to the minus 14. Well, if I replace them both with X, then I get X squared equals 1 times 10 to the minus 14. And therefore, if I solve for X by taking the square root, I get X equals 1 times 10 to the minus 7. So what that means is that in neutral water at 298 Kelvin, the concentration of hydrogen ions is equal to the concentration of hydroxide ions, and they're both equal to 10 to the minus 7 mole per dm cubed. And so on the pH scale, 7 is considered neutral. Well, why is it considered neutral? It's because that is the exponent of the hydrogen ion concentration. That's where pH comes from. So pH, you should take it to mean the power of hydrogen. It's actually, as far as I've read, it's not really clear what the P means, what the P was supposed to stand for from the person who created this scale, but we can take it to mean the power of hydrogen. And it basically means the relationship between pH and H plus is logarithmic, base 10 logs, so that every change in a factor of 10 is actually a change in 1 on the pH scale. Okay, it's also going to be somewhat inversely related because of this negative, right? So this is a negative 7. If the concentration of hydrogen becomes 10 to the negative 6, that's actually an increase in 10 times the concentration, and the pH would get lower by 1. So there's a lot of different things that sort of flip back and forth. And if we look at a few more examples, I think that will help. So the Kw always has to equal 10 to the minus 14. That means that if one of these ions' concentration goes up, the other one has to go down to compensate, so that when we multiply them together, they still equal 10 to the minus 14. So neutral water, they both equal 10 to the minus 7. If I had an acid that had 10 to the minus 6, so an increase in 10 times the H plus concentration, the effect of that would actually also decrease the hydroxide concentration by a factor of 10. So notice that the change was an increase in 10 from minus 7 to minus 6. So this was a decrease, or divided by 10 to get to 10 to the minus 8. This change here is an increase in 1,000 times. And right here is a decrease in 1,000 times. So the changes will always compensate for one another. Okay. Now, when I change by a factor of 10 in terms of concentration, I'm going to change by 1. So this means pH 7 becomes pH 6. Because now the exponent went from being minus 7 to being minus 6. So the concentration increased by 10%, or 10 times for the H plus concentration. So the pH has dropped by 1. For this one, likewise, we're going to get that pH went from being 6 and now pH is down to 3. Okay, so when we change by 1,000 or a factor of 10 to the 3, the pH changes by 3. And so the pH always matches that exponent on the H plus concentration. If we take the negative log base 10 of both sides of this equation, I get the Kw turns into the pKw, the H plus turns into pH, and the OH minus concentration turns into pOH. And 10 to the minus 14 turns into 14. So there is a corresponding value for hydroxide ions. It's just as legitimate for discussing pH or acid-base character. We tend to use pH, but really these two values are always existing at the same time, and they always have to add up to 14. So in this case, the pH was 3. I know immediately that the pOH is going to equal 11 because 3 and 11 add up to 14. And if the pH is 6, then the pOH equals 8. Okay, and so they always add up to 14, and the pOH always matches the OH minus concentration. So you can see that this is just a couple different ways to represent this, showing pH and pOH always adding up to 14, as well as some common solutions that would have these pH values. And down here, I think it's helpful to think about, here's the concentration of H plus ions, moles per liter or moles per dm cubed. So even in neutral water, remember that 10 to the minus 7th means 0.0000001 mole per dm cubed. So incredibly tiny concentrations of hydrogen ions in neutral water. Right? But that is the pH scale. The pH scale is a logarithmic scale. The key takeaways, especially at the SL level, are that it's logarithmic, meaning that changes in 10 in concentration result in changes in 1 on the pH scale. The lower you go, the more acidic something is, and the higher the concentration of hydroxide ions, of hydrogen ions, my mistake. And the higher in pH, the more hydroxide ions there are, and the more basic it is. So in SL, you only need to be able to talk about pH in those terms and be able to figure out a pH for strong acids or bases.